Sometimes a tiny, seemingly insignificant observation in a lab can ripple outwards and completely change how we see the universe. It sounds like something out of a movie, right? But it's exactly what happened with a strange little spark. Today, we're going to dive into the photoelectric effect, a phenomenon that looked simple on the surface, but wow, it ended up rewriting the fundamental rules of reality itself. So, what's the big mystery here? It all boils down to this. What did a weird little spark in a science lab have to do with the very fabric of reality? See, untangling this puzzle didn't just give us a new piece of tech. It forced us to accept a totally bizarre and frankly wonderful new picture of what light is. And in doing that, it changed physics forever.
Okay, so the plot thickens. It all kicked off in 1887. Heinrich Hertz just notices that a spark jumps across a gap a little easier when you shine UV light on it. Weird, right? A year later, Wilhelm Hauptwachs confirms it. Light was literally knocking negative charges off a metal plate. But here's where it gets really strange. In 1902, Philipp Lenard discovered that the energy of those escaping charges depended on the light's color, its frequency, not how bright it was. And according to all the physics they knew at the time, that was just impossible.
And that brings us to the main event, the big conflict. See, physics back then had this beautiful, proven idea called the wave theory of light. It treated light like a continuous, flowing wave of energy. It made sense, it worked, until it didn't. The cold, hard facts coming from the lab were about to go to war with that perfect theory. This is where the old physics just completely face-planted. The wave theory said, hey, brighter light means more energy, so the electrons that pop off should be way more energetic. But what did reality show? Nope. Brighter light just meant more electrons, all with the same max energy. The theory also said any light should work if you just wait long enough for the energy to build up. Reality? Instantaneous. It either happened right away or not at all. Every single prediction was dead wrong.
And this all led to this crucial idea of a threshold frequency. Think of it like trying to break a window. The old wave theory was like saying if you throw 1,000,000 tiny pebbles at it for long enough, it'll eventually break. But reality said, no way. It doesn't matter how many pebbles you throw. You need one single fast-moving baseball, that's your high-frequency light, to do the job. Below that energy threshold, nothing. Zilch, ever. So physicists were totally stumped for years. And then, in 1905, this young patent clerk, a guy named Albert Einstein, comes along with what he called a heuristic viewpoint. It was an idea so radical, so out there, that most physicists just thought it was ridiculous. He didn't just want to adjust the old theory. He was about to blow the whole thing up. And this quote right here is the revolution in a nutshell. Einstein basically said, what if we've got light all wrong? What if it's not a continuous wave at all, but a stream of tiny individual bullets of energy? He called them light quanta. And these little energy bullets are what we now call photons. And just like that, this one single idea, it solves everything. See, a photon's energy is tied only to its frequency, its color. A brighter light isn't more powerful photons, it's just more photons. That's why brightness knocks out more electrons, but it's the frequency that decides their energy, and there's no time delay because it's a one-on-one collision. One photon hits one electron. Boom. Instant. And Einstein boiled this whole brilliant idea down into this one beautifully simple formula. It just says that the electron's maximum kinetic energy, how fast it's moving when it escapes, is simply the energy of the incoming photon minus something called the work function. Think of that work function as the ticket price, the energy cost to escape the metal. If the photon's energy doesn't cover the price of admission, the electron's not going anywhere. It's simple, it's elegant, and it turned out to be perfectly right. Now, you can't overstate how important this was. In 1921, Albert Einstein gets the call. He's won the Nobel Prize in physics. But here's the kicker. It wasn't for relativity. His most famous theory? Nope. He won the Nobel specifically for explaining the photoelectric effect. That's how earth-shattering this discovery was. It was a cornerstone of the new quantum mechanics. Okay, so let's zoom in. What's actually happening on that tiny microscopic level when light hits metal? Well, physicists have broken it down into a pretty straightforward 3-step model. Let's follow the journey. First, step 1. Absorption. An electron inside the metal gets hit by one photon and absorbs its entire energy. It's an all-or-nothing deal. Step 2, propagation. Now this energized electron makes a run for the surface, but it might bump into other stuff along the way, losing a bit of energy. And finally, step 3, escape. If and only if it still has enough energy left to pay that ticket price we talked about, it breaks free and flies off into space. All right, I know this might all seem like very abstract, theoretical physics, but the amazing thing is, this discovery, this idea of the photon, is the foundation for technologies we use every single day. I mean, this effect is literally everywhere. It's in the image sensor of a camera you use. It's the core of how night vision goggles work. Scientists use it to analyze what materials are made of, and engineers even have to factor it in to keep spacecraft from getting zapped by sunlight. The impact is just enormous. And if you want a really cool, kind of mind-blowing example, let's look at the moon. Sunlight is constantly hitting the lunar surface and doing the exact same thing, knocking electrons off tiny dust particles. This charged-up dust then actually repels itself, and it levitates. It floats off the ground, creating this thin, ghostly atmosphere of pure dust. The Apollo astronauts actually took pictures of this eerie glow on the horizon. How cool is that?
So ultimately, the photoelectric effect was the rock that broke the back of classical physics. It was one of the very first, totally undeniable pieces of proof that forced scientists to accept a profoundly weird and wonderful idea: wave-particle duality, that light is somehow, simultaneously, both a flowing, continuous wave and a stream of individual, distinct particles. And that leaves us with a final, fascinating question to chew on. The photoelectric effect showed us that something as basic as light refuses to fit into our neat little boxes of wave or particle. It insists on being both. So it makes you wonder, what else in our universe, from the tiniest quantum bits to the grandest cosmic structures, also defies our simple labels? It's just a powerful reminder that reality is often way stranger and way more incredible than we can even imagine.